Alright, how's it going, everybody? This is my first video in a series talking about the unit circle. We're going to talk about how the unit circle is developed and how it pertains to trigonometry and sine and cosine and tangent and such as that. Today we're going to start, though, I'm going to do this in two segments. Segment 1 is going to talk about the right triangles that do this. The 30, 60, 90 triangle and the 45, 45, 90 triangle. And then I'm going to talk about in the next video how that translates over to the unit circle that's behind me right here. But what I want to talk about here, I will mention this. We have this unit circle sitting here. And if you're watching this on a computer screen, you can see this better. Right up here it says the unit circle is a circle with center at 0, 0, and the radius of this circle is 1. So you can see our x and our y-axis here, and the radius, I drew this radius is a radius of 1. So that's going to play into the discussion later, and I just want you to kind of think about that. Over here, I have up here a 30, 60, 90 right triangle, and down here I have a 45, 45, 90 right triangle. Notice that I've made the hypotenuse in each triangle length 1. That has a little bit of something to do with this unit circle over here where the radius is 1. But what I want to show you is how these sides of the triangle come about exactly. We're going to use partially trigonometry and partially Pythagorean theorem. We're going to do exact calculations, no decimals. So I know that the camera doesn't always show my face, but it's going to show the calculation so that you can see it, and I'll explain it along the way. Let's start with a 30, 60, 90 triangle. The first side that I want to find in this triangle is this side right here. I will mark it with an X. And I'm going to use trigonometry for this. If I focus on the 30-degree angle, this side is called opposite. We learned that before this nice extended break. And this is my hypotenuse of 1. So since opposite's in play and hypotenuse is in play, opposite hypotenuse is a sine. So I will write sine 30 degrees, put it over 1, equals opposite x over 1 hypotenuse. And we're going to use cross multiplication to solve that like we did in class. If we cross this way, x times 1 is x. And this is 1 times the sine of 30 degrees. In other words, it's just going to be whatever the sine of 30 degrees is. So if you were to break out a calculator that has that function and just click 1 times sine 30 degrees, you'll see that it comes out 0.5, your calculator will say. We're going to say x equals 1/2 and call it 1/2 instead of 0.5. So I'm going to replace this side with 1/2. Okay? Now, you can pause this video and look at that calculation at any time, but I'm going to obviously erase things as I go because I don't have a lot of space to work with here. Next, we're going to use Pythagorean theorem to find this missing side down here now. Because now if I use trigonometry with this side's going to come out a decimal, and I don't want it to be a decimal. I want it to be exact. And 1/2 came out nicely. This one won't be so nice. So now I'm going to call this side x for the time being, and we're going to do Pythagorean theorem, which we all know to be a squared plus b squared equals c squared. Remembering, folks, that c has to be your hypotenuse. So either of these two sides can be a or b, whichever. I'm going to call this side a, the 1/2 b, and then my hypotenuse c. So I'll be writing x squared plus 1/2 squared equals 1 squared. Simplifying that expression, I get x squared plus Folks, 1/2 squared, 1/2 times 1/2 is 1/4. And 1 squared stays 1, as we all know. Okay. Squared there. Okay, solving for x now. We're going to subtract 1/4 from each side. Folks, if I subtract 1/4, I get x squared equals 1 minus 1/4 is 3/4. And I don't want to call that 0.75. I want to call it 3/4. Because I'm going to, obviously to solve this, I'm going to square root both sides. That makes my life easier when it looks like this. If I square root both sides, I get x equals, remember from our time together, when we square root a fraction, we square root its parts independently. So we square root 3, we square root 4. Now, square root of 3, don't know that exactly, it's a decimal, so we keep it square root of 3. The denominator, square root of 4, we know that to be exactly 2. Square root of 3 over 2 is as good as we can get right there. So this side is going to be the square root of 3 over 2. So we now have a 30, 60, 90 triangle that has a hypotenuse of 1, has short side 1/2, medium distance side square root of 3 over 2. Those are exact distances. They would adhere to the Pythagorean theorem and work out nicely. Next, okay, again, pause if you want to see this calculation, if you need to write it down so you can kind of see it better. But I am going to erase this. Oh, and I wish I would have left. I'm going to leave the a squared plus b squared equals c squared part. For the next triangle down here, I'm going to go straight to the Pythagorean theorem. And here's why I can do that this time. 45, 45, 90 triangle. The 45, 45, that means these two sides, the legs, are the same length. Same angles, same length. So I'm going to call both these sides x, meaning they're the same amount. So when I go to do this Pythagorean theorem, it's going to look like this. It's going to look like x squared plus x squared equals 1 squared. Our hypotenuse is still 1. So there's that. Now, be very careful here, people. X squared plus x squared, that's like terms. That's like 1x squared plus 1x squared. So that's 2x squared equals 1. Because 1 squared is 1. Now, we're in the process of solving for x, so I know those two sides, and the same rules apply. I don't want decimals. I want exact answers only here, okay? So I'm going to divide by 2, which gets me x squared equals 1/2. And like I was in the previous calculation, I'm going to square root both sides. And this one's not going to turn out as pleasant as the last one for this reason. The square root of x squared, we get x, because the square root cancels the square. But here, square root the parts. The square root of 1, yes, is 1. That's nice. But the square root of 2 is a decimal. We leave it as the square root of 2. And you know from previous experiences, we don't like to leave a square root in the denominator. So we would multiply this by square root 2 over square root 2, giving us 1 times the square root of 2 is the square root of 2. These are both square roots, so technically square root 2 times square root 2 is square root of 4, which we know to be 2. So you guys, the x is square root of 2 over 2. That's the same for both of these over here. Square root of 2 over 2 and square root of 2 over 2. So now we have that 45-45 triangle set. square root of 2 over 2, square root of 2 over 2, 1. And our 30, 60, 90, 1/2, square root of 3 over 2, and 1. Now, I'm going to just transition into the next part, but I'm going to stop there and kind of treat the unit circle in its own area. Right here, I have two triangles cut out that are basically these two. They fit up here perfectly. Okay? That one's right on top of that one, and this one is right on top of that one. All right? Here's the deal, that the transition we're going to make. This triangle, the reason I made the hypotenuse 1 and I had set the hypotenuse as 1, I'm going to be placing this triangle right here on this unit circle. So notice I'm placing the 30-degree angle at the center of the unit circle at 0, 0. The hypotenuse of 1 is a perfect radius right to the edge of this circle. And I'm actually going to put a dot right there for right now, because this is where my discussion is going to pick up in the next piece of the video. Because the question I'm going to lead off with on the next video is, if this triangle, which is the 30-degree angle here, and we have a circle, obviously we can go around this circle a total of 360 degrees if we go one revolution. First of all, I want to know how much rotation is it this far. And if the sides of this triangle, our hypotenuse is 1, this side is 1/2, and this side is square root of 3 over 2, what are the coordinates of this? And what do the coordinates mean anyway? Why is it important that I know those coordinates? They mean something, but why is it important? And then lastly in this part of the video, and I'm going to be using this triangle a lot in this circle here eventually, the 45, 45, 90 will take on the same role. It'll be going right here. This time I put the 45-degree angle at the middle, and that puts me a point up here. So we're going to talk about how many degrees is that rotating. What are the coordinates of that point? If the sides of this triangle are square root of 2 over 2, square root of 2 over 2, hypotenuse of 1, we're going to talk about all that stuff. And you guys, when all's said and done, so if you kind of, if I look right now, I got 2 dots on this, one right there and one right there. When all's said and done, we're going to have about 16, 17 dots on here. And there's going to be angle measurements, and there's going to be these radian measurements. We talked about that before the break. And there's going to be a whole bunch of coordinates. And, so what? What's all this for? There's a reason in trigonometry, and we're going to talk about what those are needed for. And in talking closely with the calculus teachers, they're like, kids better know this when they walk in the door next year. Like, they should walk in the door for calculus and know the unit circle inside and out. And I hesitate to use the word memorize, but having the patterns in your head to do this. And in the next video, that's what we'll talk about.